Hello guys, welcome on Tesla Adventures. In this video, we'll be discussing level 2 numericals based on elasticity and stress, strain and Hooke's law. So in this first question you can see that there are three blocks A, B and C. Each of them has a mass of 4 kg and they are attached with these wires as shown. So both of these wires have equal cross-sectional area, which is 5 into 10 raised to power minus 7 meter square, and this surface is smooth. So we have to find out the ratio of longitudinal strain developed in the two wires, which is strain in 1 upon strain in 2. So first of all, we know that strain is equal to stress upon Young's modulus, and the Young's modulus of both the wires is same. So just we have to find out the ratio of strain. So strain in 1 upon strain in 2 will be equal to stress in 1 upon stress in 2. So Young's modulus of each of them is same. Now the area of cross section of both of these wires is also same. So stress in 1 will be tension in wire 1 upon area, and stress in wire 2 will be tension in wire 2 upon area. Now we know that area is also same, so we can just eliminate the area, and therefore we can find out the acceleration of the system. So by a short trick which we have already discussed in NLM section, that the acceleration of this system would be net pulling force. So we can see that this system is being pulled by the mg of this mass, which is 40, because its m is 4 kg, so mg is 40 upon total moving mass. Now total moving mass is 4 plus 4 plus 4, which is 12. So the acceleration of this system will be 10 by 3. Okay, so let us find out the tension in wire 2. This is T2. So for T2, we can see that the free body of C, free body diagram for C. So for C, the equation will be mg minus T2 is equal to ma. And mg of C is 40 minus T2 is equal to 4 into 10 by 3. So T2 will be equal to 40 minus 40 by 3, so it is equal to 80 by 3. Now T1, this is T1, and the acceleration of block A is also same A, so T1 will be equal to ma. I am writing it for block A, for block A. Now T1 is m into A. M is 4 and A is 40, 10 by 3 in fact. So T1 will be 40 by 3. Now we have to find out the ratio of T1 and T2. So T1 and T2 will be 40 by 80. So it is equal to 1 by 2. So the ratio of the longitudinal strains developed in these two wires is 1 by 2. Thank you. Now we move on the next question. In this question, there are two exactly similar wires, one of steel and one of copper. So exactly similar means in dimensions, not in materials. And their difference in elongation is given as 0.5 centimeter, which means that when we have applied the same force on them, then they have elongated differently, and the difference of their elongation is 0.5 centimeters. So we have to find out that how much each wire has elongated, and it is given that the Young's modulus for steel is 2 into 10 raised to power 12, and Young's modulus for the copper is 12 into 10 raised to power 11. And you can see that the unit system which is used in this question is CGS. So we can use this system throughout in the question. So it is not needed to convert this system into MKS. So we are using this system throughout in the calculation. So we know that strain, or we can say that delta L by L, which is strain, is equal to stress, which is force upon area, and upon Young's modulus, because stress upon strain is Young's modulus. So delta L is equal to F into L upon A into gamma. Now let us write down that delta L1 is equal to, let us name this term as C, some constant C, because F, L and A is same and gamma is different, so it is 1 by C by gamma, and delta L2 is equal to C by gamma 2. Now we can easily see that this elongation is inversely proportional to the Young's modulus. So therefore we can conclude that the wire which has greater Young's modulus will be having lesser elongation. So you can see that this wire has a elongation of the Young's modulus of 1.2 into 10 raised to power 11, and this wire has a elongation of, in fact I am writing it down, that gamma of steel is equal to into 10 raised to power 12, and gamma for copper is 1.2 into 10 raised to power 12. So we can see that gamma of steel is greater than gamma of copper. So we can say that delta L of steel will be less than delta L of copper, because delta L is in inverse relationship with gamma. So the net extension is delta L of copper minus delta L of steel, and it is equal to C, which is common, 1 upon gamma of copper 1.2 into 10 raised to power 12 minus 1 by 2 into 10 raised to power 12. So we can take it out common, and this is equal to 1 by 2 centimeter. The unit system which we are using is CGS. So this is 10 raised to power 12, and this is 10 by 12 minus 0.5. Okay. So this is 1 by 2 and C by 10 raised to power 12, and this is 12 and 10 minus 6. So it is equal to 1 by 2 C by 10 raised to power 12, and this is 4 by 12, which is 1 by 3. So C is equal to 1.5 into 10 raised to power 12. This is the value of C. So now we have to find out the elongation in each of them. So we can say that the elongation delta L in steel will be equal to C upon gamma steel. So delta L of steel is equal to 1.5 into 10 raised to power 12 upon gamma of steel, which is equal to gamma of steel is 2 into 10 raised to power 12. So this is 2 into 10 raised to power 12. So cancelling this out, so this will be equal to 3 by 4. Okay, centimeter. And delta L of copper will be equal to 1.C by gamma of copper. So C is 1.5 into 10 raised to power 12, and gamma for the copper will be 1.2 into 10 raised to power 12. Cancelling this out, this will be 15 by 12, which is equal to 5 by 4. Okay, so we have to also find out the ratio of elongation in copper to elongation in steel. So delta L of copper upon delta L of steel will be equal to 5 by 4 upon 3 by 4. So this will be 5 by 3, and if we compare it with 5 by x, so it would be x would be equal to 3. Now let's move on the next question. In this question, it is given that there is a spherical ball which contracts in volume by 0.001%. So we can see that delta V by V is equal to in fact in percentage is equal to 0.001%. So delta V by V will be equal to, this is 10 raised to power minus 5. You can see that that this is 1 into 10 raised to power minus 3 and 10 raised to power 2 will be coming in denominator. So delta V by V is 10 raised to power minus 5. Now pressure, we know that the volumetric pressure is also, volumetric stress is also called as pressure. So volumetric stress will be equal to pressure, and pressure is equal to 100 atmosphere, which is 10 raised to power 2 atm, and 1 atm is 10 raised to power 5 pascals, so it is 10 raised to power 7. Now the bulk modulus, we know that stress upon strain, volumetric stress upon volumetric strain is bulk modulus. So this is bulk modulus, and volumetric stress is 10 raised to power 7, and the volumetric strain is 10 raised to power minus 5. So this is 10 raised to power 12. So we have to find out this in ATM, atmospheres. So we can say that it is 1 into 10 raised to power. In fact, you can see that this is 10 raised to power 12 is equal to 10 raised to power 7 ATM, because 1 ATM is 10 raised to power 5 Pascal. So this is the bulk modulus, and therefore bulk modulus is equal to 1 into 10 raised to power 7 ATM. You have to find it out in ATM. So x, the value of x in this case is equal to 1, and this is the final answer. Now let's move on the next question. In this question, it is given that there is a metal rod of Young's modulus, which is 2 into 10 raised to power 10, and it undergoes a elastic strain of 0.06%. So we have to find out the energy stored per unit volume in the metal wire. So we can see that gamma is equal to 2 into 10 raised to power 10. Strain is equal to 0.06%. So strain will be equal to 6 into 10 raised to power minus 4. Why I am writing down this as 10 raised to power minus 4? Because it is 10 raised to power minus 2, but it is in percentage. So I have to write the absolute value of strain. So it is 6 into 10 raised to power minus 4. Now the energy density, which is energy per unit volume, has a formula of half stress into strain. And we can understand this fundamental logic that if the only thing which is given in this question is strain and Young's modulus, and stress is not given, so we can eliminate stress by writing it down as stress is equal to strain into gamma. So this formula becomes half strain whole square into gamma. So this energy density is half strain whole square is 6 into 10 raised to power minus 4 whole square into gamma, where gamma will be 2 into 10 raised to power 10. So cancelling this 2 with 2, so energy density is, this is 36 into 10 raised to power, this is minus 8 and into 10. So this is 10 raised to power 2. So U is equal to 3600. So if we compare it with 600x joule per meter cube, so we can see that x is equal to 6. So the correct value of x is 6. Now we'll move on the next question. In this question, there is a metal wire of length L, and it is suspended vertically with a rigid support from a rigid roof support, and a bob of mass m is attached to its lower end. The elongation due to that mass m in the wire is L. Therefore, we have to match up the following column 1 with column 2. So we can see that the extension produced in the wire is L. Therefore, the mass m, which is suspended from the wire, has moved down by a distance of L. Therefore, the loss in gravitational potential energy of M will be mg L, and therefore the correct option for this first one is P. Okay, now the second option says that the elastic potential energy is stored in the wire. So the elastic potential energy is equal to half F into X, where F is the force pulling the wire and X is the extension. So it is equal to half F is mg and X is L. So mgl by 2. So the correct option for this one is Q. Now the elastic constant of the wire is equal to K, and it is gamma A by L. But we have only given with this K. So K can be written as mg by X. We are writing F is equal to Kx, and therefore K is equal to F by X. So F is mg and X is L. So mg by L, the option number R. And the heat produced in the extension is always equal to the elastic potential energy stored. So the heat produced will be equal to the energy stored. So it is mg L by 2. So the correct option for option number 4 is also mg L by 2, which is option number Q. Thank you. In this question, it is given that there are two rods which are identical in shape and size, but their material is different. Their coefficient of thermal expansion is alpha 1 and alpha 2, and their Young's moduli are gamma 1 and gamma 2 respectively. These rods are separately fixed between two walls one by one, and they are subjected to same rise in temperature. It is observed that there is no bending in the rods, and it is given that the ratio of alpha 1 and alpha 2 is 2:6. So we have to find out the ratio of gamma 1 and gamma 2, provided that the thermal stress developed in both the rods is equal. Now we have already discussed the topic of thermal stress, and we know that thermal stress is equal to alpha gamma delta T. This we have already derived. So it is given that their thermal stress is equal. Therefore, alpha 1 gamma 1 delta T is equal to alpha 2 gamma 2 delta T. Now if we eliminate delta T, then we can see that alpha 1 by alpha 2 is equal to gamma 2 by gamma 1, and alpha 1 by alpha 2 is given 2:6, which is 1 by 3. So gamma 1 by gamma 2 is equal to 3:1. So this is the required answer. Now let's move on the next question. In this question, you can see that there is a 1 meter long wire, which means its length is 1 meter, and the area of cross section of this wire is 10 raised to power minus 6 meter square. It is fixed from one of its end with roof, and the other end is suspended with a weight of W, and this graph shows the observations of delta L plotted with weight, and we have to find out the Young's modulus in standard units. So we know that force upon area, which is weight upon area, is equal to delta L by L into gamma, and W is equal to delta L gamma A by L. Now this is delta L is equal to L by gamma A into W. Now you can see that it is plotted in y-axis and it is plotted on x-axis. And the slope of this graph is this one. So slope is equal to L by gamma A. and slope is also equal to delta y by delta x. So you can see that if we find out this height, then it is 5 minus 1, which is 4 into 10 raised to power minus 4, and this length is 100 minus 20 is 80. So this is equal to, slope of this graph is equal to 4 into 10 raised to power minus 4 upon 80. So this is 1 by 20 into 10 raised to power minus 4, and therefore it is 0.05 into 10 raised to power minus 4. So you can write it down as 5 into 10 raised to power minus 6. Okay, so this is the slope of this graph, and this slope 5 into 10 raised to power minus 6 is equal to L upon gamma A, where L is 1 and gamma we have to find out, and area of this wire is 10 raised to power minus 6. So the gamma will be equal to 1 by 5 into 10 raised to power 12. So this is 2 into 10 raised to power 11. So the correct answer will be option number C. Now we move on the next question. In this question, there is a mass of value 0.1 kg and it is suspended from a wire of negligible mass. The length of the wire is 1 meter. This is 1 meter. And the area of cross section of the wire is 4.9 into 10 raised to power minus 7 meter square. This mass is suspended with this wire in vertical plane, and this mass is being pulled by a slight amount and it is released. Then it performs simple harmonic motion of angular frequency 140 radians per second. So the Young's modulus of the wire will be n into 10 raised to power 9. We have to find out n. Now we know that if we assume this wire as an analogous spring, then angular frequency of the spring is under root k by m. We know that. And the value of k is equal to gamma a by L. So first of all, let us find out the value of k. So k is equal to m omega square. So this mass is 0.1 and omega square will be 140 whole square. So this will be 19600 into 0.1. So the value of k will be 1960. Now we have to find out the value of gamma. So 1960, which is k, is equal to gamma into the area. Area is 4.9 into 10 raised to power minus 7. And the length is 1 meter. So gamma is equal to, this is 19.6 into 10 raised to power 2 and divided by 4.9 into 10 raised to power minus 7. So gamma is equal to 4 into 10 raised to power 9. This is the value of gamma. So the value of n in this case would be 4. So n is equal to 4. Now we move on the next question. In this question, there are two wires made up of same material, and the volume of these wires is same. The wire 1 has a cross section area of A and wire 2 has a cross section area of 3A. If the length of the wire is increased by delta x on applying a force F, then how much force is needed to stretch the wire 2 by the same amount? So we can see that the force upon area is equal to delta L by L into gamma. The material of the wires is same, therefore gamma is same, and F is equal to delta L gamma by L into area. Now if I multiply both the sides with A, so you can see that F becomes delta L gamma A square by V, where A into L is volume. Now we can see that F1 for the wire 1 will be delta L. We have to produce same extension in both the wires, so delta L will be same. As the material of the wire is same, therefore gamma will be same, but area is different. So this is A1 square by volume is same. So we can see that F1 is this and F2 will be delta L gamma A2 square by V. So F1 by F2 will be equal to A1 square by A2 square. Now F1 was equal to F and F2 we have to find out, and A1 was equal to A, while A2 was equal to 3A. So this is 9A square. So F2 is equal to 9F. So the correct answer will be option number 3. Now we move on the next question. In this question it is given that there are two wires. One wire is thick wire of radius 2r and length 2l, and the other wire is thin wire of radius r and length l. These are welded together, and this arrangement is stretched by applying some force on both the ends. So we have to find out the ratio of elongation in the thin wire to the thick wire. Now let us assume that this is a thick wire and here is the thin wire. Okay, so we are assuming that these wires are analogous to springs. So this is spring number 1 with coefficient K1 and this is spring number 2 with coefficient K2. Now K1, these are stretched by applying force on the ends. Obviously this force will be equal. Okay, otherwise this system will start to accelerate and there is no data given for acceleration, and springs are also considered to be massless as wires are considered to be massless. So we know that if force in the wires will be same, in the spring will be same, therefore K1 x1 will be equal to K2 x2, where x1 x2 are the elongations. So this is a thick wire and this one is thin wire. So we have to find out the extension in thin wire to the extension in thick wire. So we have to find out x2 by x1. So x2 by x1 will be equal to k1 by k2. Now you can see that one wire is of copper and other wire is also of copper. Therefore gamma will be same, and we know that k is equal to gamma a by l. So this k1 by k2 will be equal to a1 by a2 upon this is l1 by l2. Now the area of the first wire is the area of this one k1 is equal to 4 pi r square, because its radius is 2r and the length of the second wire is l. The area of the second wire is pi r square and the length of the second wire is length of the first wire is 2l. So cancelling out this l with l, this pi r square with pi r square, so you can see that x2 by x1 is equal to 2. So the correct answer will be equal to C. Now we move on the next question. In this question it is given that there is a solid sphere of radius r which is made up of a soft material of bulk modulus k. So in this question there is a situation in which there is a piston whose area of cross section is A, and there is a solid sphere of some radius r floating in this liquid. So this is given that the mass of the piston is 0, It is a massless piston and area is A. And it covers the entire cross section of the cylindrical container. So it is given that when a mass of M is kept on this cylinder, then it compresses the liquid and hence it compresses the cylinder. This is sphere which is floating inside it, and the fractional decrement in the radius of the sphere is dr by r. So we have to find out the value of dr by r. Okay, so we know that the additional mass which is kept on this piston is mg. So additional stress developed due to this mass will be mg by area and it would be equal to bulk modulus into the change in volume upon original volume. Now we know that volume of a sphere is 4 by 3 pi r cube. So dV will be equal to 4 pi r square dr. I have differentiated this one. So dV by V will be equal to this is 1 dr by 3 dr by r. You can see that dV by V is equal to 3 dr by r. So mg by area is equal to bulk modulus into 3 dr by r and therefore dr by r is equal to mg by 3a bulk modulus, and bulk modulus here is given as k. So the correct answer will be option number A. Now we move on the next question. In this question, it is given that there is a pendulum whose it is connected with a wire whose area of cross section is A, and it is oscillating with a time period of t. When additional mass m is added to this pendulum ball, then time period changes to tm. Now you must be wondering that why time period of pendulum changes due to some additional mass. Although its time period does not depend on the mass. It is due to the fact that when some additional mass is suspended with the thread of the pendulum, then it is elongated, and due to its elongation its length changes and therefore its time period changes. Now we can see that delta L is the change in length of the pendulum wire upon original length is equal to stress, which is mg by area upon gamma, and delta L is equal to mg by a gamma into L, and the new time period will be 2 pi under root L plus delta L by G. You can see that this Tm by T whole square is equal to L plus delta L by L. So Tm by T is equal to 1 plus delta L by L. So it is 1 plus mg by a gamma. So we have to find out 1 upon gamma and therefore mg by a gamma is equal to, this is square, is equal to 1 minus Tm by T whole square, and 1 by gamma is equal to a by mg into 1 minus Tm by T whole square. So this is the value of 1 by gamma. So the correct option will be in fact this is minus 1 and this is plus. So the correct option will be option number 1. Now we move on the next question. In this question, it is given that when we have loaded a wire with 2 kg weight, then the elongation was 0.6, and when we have increased the weight by 4 kg weight, in fact we have increased the final weight to 4 kg weight. So the final weight is 4 kg weight. And then elongation becomes 1 mm. So we have to find out the work done in extending this wire from 0.6 to 1 mm. So let us write down the formula first of all. So by spring analogy, we know that we have given with force with which we are extending the wire and the extension produced in the wire. So we will use the formula of energy as half F into X. So the change in energy will be half F1, in fact F2 X2 minus F1 X1. So half. Now the final weight was 4 kg and this is 4 kg into 10, which is the acceleration due to gravity, which is 40. So there it would be 40 into 10 raised to power minus 3, which is the final extension. And the initial extension was equal to 0.6. So minus of F1, which was 2 into 10, which is 20, and 10 raised to power minus 3 into 6.6. So this is half into 10 raised to power 3, and this is 40 minus 12. So this is equal to 28 by 2 into 10 raised to power 3. So it is 14 into 10 raised to power 3. And if we compare it with 2x into 10 raised to power, in fact this is minus 3. Okay, so this is minus 3. So x will be equal to 7. So the correct answer will be 7. Now we move on the next question.